Hi everyone, this is Martin Shkreli, and this is chapter 13 of the Zumdahl and Zumdahl chemistry textbook we're reviewing, pages 606 to 651. This chapter is called Chemical Equilibrium, and we're going to build on what we learned in chapter 12. Okay, so what is chemical equilibrium or just equilibrium? Well, it's an important concept that we're going to need in chemistry. Um, and basically, it's a state where all the concentrations of all the products and reactants remain constant with time. So basically, everything comes to, all the changes in the system come to a stop. It doesn't mean that the system is static, and we'll talk about that in a second, but it does mean that the concentrations will stop shifting. So in essence, they've reached equilibrium, and it sort of sounds like it is what it sounds like, right? I mean, it's reached an equilibrium. We've talked about equilibriums or equilibria colloquially, so just keep that in mind. All right, so we have this dimerization reaction where nitrogen dioxide combines with another atom of nitrogen dioxide to form this N2O4 species, dinitrogen tetraoxide, I guess. And what's interesting about it is we've learned in the past that nitrogen dioxide is this brown gas, while N2O4 is colorless, and that's a pretty interesting idea, right? You can have two separate molecules are both brown gases, but when they combine, they're colorless. Pretty fascinating. Anyway, if we put any amount of reactants in a closed container, that system will reach equilibrium. And this is a pretty important concept to get through. And we're going to talk a lot about this, and one of the things to consider is that you're going to have some reactions that the products will form from the reactants, and you'll have some reactions where the reactants don't really form many products. And the way we're going to describe that is talking about the equilibrium position. That concept of an equilibrium position, we can define it as whether or not the products will be converted from the reactants, or the reactants will kind of not do too much conversion. So if the reactants kind of stay the same, we're going to say that the equilibrium position lies to the left, towards the reactants, and that kind of makes sense since it's the left of the reaction arrow. And if all of the reactants are consumed and become products, we're going to say that the reaction lies far to the right, in the direction of the products. And so, what might surprise you, I guess, is that if we do have a closed container, that all systems in a closed container will reach equilibrium. And part of the reason that that's somewhat surprising, maybe to even me, is that we learn a lot that these reactions are kind of one-directional, and that they proceed to completion. But the reality is there is the reverse reaction in addition to the forward reaction, and that impinges on virtually every reaction. We'll talk a little bit about that dynamic. Even if 99.9% of the activity is going in the direction of the products, there's still some equilibrium, and we'll discuss that further. So I made these charts. I hope you appreciate them. I worked hard to make them. You can see the craftsmanship and quality of these charts. But let's talk about what we mean by the equilibrium condition. I'm going to open up my Zumdahl textbook just so I can review it and read from it. All right, so as I mentioned a slide ago, the equilibrium is still a dynamic situation, even though there's no changes. As you can see here, in this situation, it reaches this reaction reaches equilibrium, and here we just have a simple water and carbon monoxide becomes hydrogen and carbon dioxide, and you can see this fancy symbol. And I would encourage you to practice writing that fancy symbol. It is a very impressive looking symbol that you don't see every day, and if someone sees you scrawling it on a piece of paper, they might think that you're doing something very dangerous. But it's just a sign that means equilibrium, and it basically means that the system is in equilibrium and that the forward reaction and the reverse reaction are equal. And so let's see what that means. So here you have the red line represents the products, and the black line represents the reactants, and this is pretty simple. We start just like we learned last chapter. We start with water or remember they're in equal molar concentrations here. 1 mole of this and 1 mole of that, or 1 atom of molecule of this and 1 molecule of that. So it's water and carbon monoxide, and you can see that they get consumed, and they become this product, which is either carbon dioxide or hydrogen diatomic gas. And you can see that this reaction lies pretty far to the right. Most of the reactants will be consumed, however, not all. And you'll see that they reach this asymptotic point where there is this equilibrium, and they will not change any further. There'll still be some carbon monoxide in water, and it won't get converted to carbon dioxide and hydrogen gas. So, in this situation, the equilibrium lies far to the right. In this little graphic I made, what's kind of interesting here is you can see that the forward rate, the forward rate, in other words, the consumption of these reactants into these products, is very fast. And the reverse rate is not really taking place because if we start with the reactants, we're not going to have any products to go in reverse. So the reverse rate will pick up steam, and when these rates equal, that's when the system reaches equilibrium. And that's kind of an important concept. All right, 13.2. We're going to learn something really, really important here. I joke that it's the things that we really need to know, we tattoo. And this is your next chemistry tattoo. I don't remember all the tattoos we've done, but hopefully you're not running out of space, and this is an important tattoo. It's called the law of mass action, and it's going to be something we're going to use for the rest of this chapter and maybe the rest of our lives. So, in any event, this is a description of the equilibrium condition. We have these coefficients. We have the species, which are the reactants in this case, A and B, and their coefficients J and K, and we have the equilibrium sign, and then we have the products C and D and their coefficients L and M. And so the law of mass action is the following. And maybe I should blow this up. Let me do that. All right. That's better. The law of mass action gives for this form. Let me make these both really big because you need to know this. The law of mass action gives for these products and these reactants, it gives the equilibrium state with the following. And K is what we'll call the equilibrium constant. And this is how we derive that equilibrium constant. So let's take it into, let's do a practical example. So here we have 4NH3 plus 7O2. Did I miss I think I missed a equilibrium sign. Let me add that real quick. Here we go. All right. So becomes 4 nitrogen dioxide and 6 water. It can be expressed as the following. So we're going to take the products and we're going to put them on top. And their coefficients then become their exponents. And that's all divided by the reactants, and their coefficients become their exponents. So that's sort of how we do it, and these are the concentrations. So we can actually put the concentrations in if we know them. So if there's 1 molar of nitrogen dioxide, or 1 mole I should say, we can put 1 in there. If there's 2 moles of water, we can put 2 in there, and so forth and so forth. And we're gonna do this example in a second, but this is how we set up the law of mass action. All right, so let's do our first problem. And this is on page 611 in the book. So we have this example. This is the Haber process to make ammonia. And we basically have this diatomic nitrogen gas with diatomic hydrogen gas, and with a little bit of heat, you can actually make ammonia. And this is the process that's used in real life. And so here we have this the following concentrations. We have 3.1 times 10 to the negative second moles per liter of ammonia. We've got 8.5 times 10 to the negative 1 moles per liter of nitrogen. And we've got 3.1 times 10 to the negative third moles per liter of hydrogen. So we need to calculate the value of K at this temperature. And then they also want us to calculate the value of K for the reverse reaction. And then they want us to calculate the K value for sort of a half, basically a half of the top reaction. So we're going to do this. That's pretty easy. The Haber process is, as we can see, this simple equilibrium here, and it does reach equilibrium, like all reactions. And K, we can see again, we take the product and we put it on top, and we're going to square it because the coefficient is 2. And that's sort of like calculus. You take the, in calculus, you take the exponent and you put it as the coefficient when you take a derivative. And this is sort of like taking the antiderivative. You take the coefficient and you put it as the exponent. And then we do the same thing for the reactants, except we put them in the denominator. And so here, N2, well, there's a coefficient of 1, right? There's always a coefficient. Sometimes you don't see it. So coefficient is 1. We're taking it to the, I guess, to the 1th power, first power. And then here, 3 diatomic hydrogens, we put hydrogen here, and we're taking it to the 3rd power. And so if we do that, we remember these concentrations. We have 3.1, 8.5, and 3.1 to their respective molar concentrations. So 3.1 times 10 to the negative second. We're going to put that here, and we're going to square it, because remember the coefficient of ammonia is 2. And we do all this math, and we get 3.8 times 10 to the 4th is the equilibrium constant. And note there's no units. Equilibrium constant is just the equilibrium constant. And now for the reverse reaction, we actually are just going to do, right, we're going to do the reciprocal, which makes a lot of sense. We're just going to take 1 over k, and we get the equilibrium constant for the reverse reaction. We're going to see why getting the equilibrium constant is really valuable. As you can imagine, knowing the equilibrium constant allows us to know other things, and we've seen that in other areas of chemistry. So let's keep going here. All right. And so here we have the sort of half reaction of the Haber process, right? And so we'll call this K double prime. And if we do that, do all the math out, we know that K double prime is equal to K to the 1/2 power, the square root of K. And we can see that here. And the square root of 3.8 times 10 to the 4th is actually 1.9 times 10 to the 2nd. So that's a pretty easy way to do this. And if you notice, K double prime is this half reaction, and the prior reaction was just K, so this made a lot of sense mathematically. Okay, so let's go to this problem. So this is the rest of this equilibrium constant part of this chapter. And one of the things that's going to be fascinating about the law of mass action is we're going to get the same K value no matter how much of the gases we mix together. And that could be a little counterintuitive. So here's 3 experiments with the same reaction, the Haber process, and totally different concentrations. So here we have no ammonia. No ammonia. All we've got is nitrogen, hydrogen. Here we have only ammonia, and it's going to decompose. And here we have a little bit of all 3. And you can see that no matter what, the K value is going to be the same. And if you don't trust me, you can go ahead and do the math. But these will be the equilibrium concentrations at equilibrium after the reactions had some time to progress. And the K value will be the same no matter what. So the equilibrium constant is truly a constant, which makes sense. Trying to figure out why I wrote the equilibrium constants are not always the same. Let me see here. How did I write that? I think the equilibrium positions, maybe. That's what I meant to write. I think that's it. All right. Great. Okay, so the book gives another example, and you're welcome to do it. And it has to do with, let's see, sulfur dioxide and sulfur trioxide. And you're welcome to do that one. But before we move on to 13.3, there's what we'll describe as the equilibrium position. And these are the equilibrium positions for these initial concentrations. And so the equilibrium position depends on the initial concentration. And so therefore there are an infinite number of different positions you can have, but there's only one constant, and it never depends on the concentration, which is super interesting because you could have 100 moles of the products and no moles of the reactants, and you'll still reach an equilibrium, and that equilibrium will still depend on the K, the equilibrium constant. So that's really really important. All right, let's move on to 13.3. So here are a way to deal with equilibrium positions and pressure. And so we can use Kp as sort of a pressure constant, and we can use the law of mass action in the form of pressures. So we can take partial pressures, I love saying that, partial pressures of ammonia for the Haber process, and we can see that these partial pressures will also be at equilibrium. So here's another reaction where we take nitrogen monoxide, or nitric, and then we add chlorine gas, and we get this NOCl. I'm not sure what that is. I think it's nitrosyl chloride or something like that. And anyway, let's see here. Yeah, nitrosyl chloride. And we can calculate the Kp from these partial pressures, which is kind of cool. So here they're giving us the partial pressure of nitrosyl. The product is 1.2 atms. We can see that the partial for nitric is 5.0 times 10 to the negative 2 atms, and we can see the partial pressure for the chlorine gas is 3 times 10 to the negative 1 atmospheres. And so if we do the partial pressures in the form of the law of mass action, remember the coefficients will become exponents, right? So we'll start with the product, which is how we do laws of mass action. We put it over here, and we have to square the pressure because the coefficient is 2. And then we do the same thing here. We take the nitrogen, and I put NO2, but it's not NO2. It's just nitric. We take the nitric, and we square that because the coefficient is 2. And then we just multiply it by the chlorine because there's coefficient is 1. And we get 1.9 times 10 to the third power is the equilibrium constant of pressure, or the pressure equilibrium constant. What's kind of cool is we know from our first chemistry tattoo, PV equals nRT, the Kpk relationship is the following. It's Kp equals K times RT to the delta N. And delta N is the sum of coefficients of the gaseous products minus the sum of coefficients of the gaseous products. Because what's interesting in equilibrium is and we'll talk about this just in the next slide, is that we find that the gaseous products obey these laws, but the solid and liquid products and reactants do not. So we're going to learn more about that in a second. But you can use these. You can sort of equate the Kpk relationship using the PV equals nRT. So we'll talk about heterogeneous equilibria, and don't worry if some of this is a little bit complex for you. This is a chapter. When we were doing this review ad hoc, I actually skipped this chapter because I felt it was a little dense and not relevant in the real world. Then I sort of decided you really can't learn chemistry without learning the law of mass action. But once you learn the law of mass action, I think, and apply it at least once or twice, I think you'll be okay with respect to chemistry, especially with respect to medicinal and organic chemistry, especially if you're not going to focus overwhelmingly on synthesis. So in any event, let's continue. Okay, so when all the reactants are gases, this is homogeneous equilibria. But if we have different phases, we're gonna talk about heterogeneous equilibria. And here we have a pretty cool little reaction. So we have calcium carbonate, and then we have what we'll call lime. Calcium carbonate will decompose into lime and carbon dioxide. And what we find is that the equilibrium position is not dependent on how much solid or liquid there is in the reaction. So here's the only gas. The rest of these are solids. So the equilibrium constant here is just K equals the concentration of KO2. So we're not going to include concentrations of pure liquids or solids in equilibrium expressions, which is pretty fascinating. Pretty fascinating. All right, so I also used my graphical skill here to teach 13.5. Now 13.5 is interesting. You have a fictional reaction of three of these blue guys, and as a reactant, and one blue guy and one purple guy become this. You can think of this, I guess, as like a carbon dioxide or something like that, plus two blue guys. So two blue and one purple become two blue and just two blue. So this trimer becomes a dimer, and this mixed species becomes this species. It's pretty interesting. Okay, so in any event, these graphics are amazing. And this reaction is a really interesting equilibrium constant of 16. 16. Okay, and so the book tells us that we're given 9 of this trimer and 12 of this, I guess, heterodimer. And the system reacts and comes to equilibrium. What will the system look like? And this was one of the hardest problems that I've had to do. It's a huge amount of effort. And what we did is we used, of course, the law of mass action. And so 5 of the reactants disappear and 5 of the products appear. We would go from 9, so we just pick 5 randomly. We say, okay, let's say 9 and 12 go to, I don't know, 4 and 7, all right? And the reactants go down, right, from 9 and 12 to 4 and 7, and the products go from 0 and 0 to 5 and 5. And so if we put these numbers in the law of mass action, we get the wrong equilibrium, right? We get the wrong equilibrium number. Let's try that out. So the products are 5 and 5, right? We just picked it out of the hat. And the equilibrium position for the reactants are 4 and 7 because they go from 9 and 12. You subtract 5 from each and you get 4 and 7. And we know 5 times 5 is 25 and 4 times 7 is 28, and that's approximately 0.9. But they told us the K value is not 0.9. It is actually 16. It's 16. So we have to fix this. How do we fix this? Well, we did this really elaborate quadratic equation, which was, I will tell you, was painful and required many of my streamers to help me with. But it was basically this. We took an unknown because we wanted to figure out what the unknown products were. So we took the unknown and we put in the law of mass action, and then we said, well, the reactants will drop by that number of products. And that makes sense, right? We have 9 to start with, so if it becomes X, if 9 of the products turn into X, then the amount of product left, or the reactant left, 9 of the reactants turn into X products, so the amount of reactants left will be 9 minus X. That makes a lot of sense to me. And the same thing goes with the other species. So we have to solve this for 16. And it turns out this is pretty hard. This is pretty hard. We have to move this guy over here, then we have to use the quadratic equation, and a lot of people got it wrong, but eventually we learned that X is equal to 8. X is equal to 8. And the equilibrium lies far to the right. That means there's only, of the trimer, 9 become 8. There's only one of these guys left over, so the reverse reaction is not contributing very much, and that's why the equilibrium constant is so large. And what's interesting is when we did it the first time, it's kind of fun. What's kind of fun here is we did it the first time, we said, all right, maybe 9 of the trimer, I'll draw it again, and 12 of the dimer, I don't know, maybe they become, and we were guessing, right? We said maybe they become 5. 5 and 5, that seems reasonable, right? 5 and 5, so this one will drop from 9 of them to 4 of them, and this will drop from 12 of them to 7 of them. And that's what it'll look like. It starts out as 0 and 0, right? Starts out as 0 and 0, and so we guessed that maybe it'll become like half of them will move over. And when we did that math, the 5 and 5 and the 4 and 7, and we got 25 over 28, and we said, okay, that's 0.9. You punch that into your calculator, you do it in your head, and you say that's K equals 0.9, but they told us K equals 16. So you said, what has to happen here? This numerator has to be way higher, and this has to be way lower. And what does that mean? Well, the reactants are in the denominator, right? Reactants are in the denominator. So the reactants have to go down, and the products have to go up. So that means the reactants have to be consumed. They have to disappear. And that's why when it's something like this, 1 over 16, that means K equals 16. When it's 2 over, 12, well, they're getting closer, but the reactants still have to disappear and become products. And that's sort of the nature of these equilibrium constants. So that's a pretty cool, easy way to sort of look at eyeball K and say, if the value of K is a lot larger than 1, the equilibrium will lie, values of K larger than 1 mean the equilibrium will be towards the product. Lies to the right. So a very large equilibrium constant means the reaction mostly goes to completion. There's very little, very, very, very little reactants left. At a very small K value, say 0.0001 or something like that, 1 times 10 to the negative third or fourth, that means that the system will mostly stay in reactants and there won't be much products. And that means the equilibrium position lies to the left. So the reaction basically doesn't happen to any appreciable constant. And notice the size of the K value has nothing to do with the time, the reaction rate, nothing to do with it. It just tells you where the concentrations will be at equilibrium. All right, we're almost done here, a couple more slides. And we're going to learn something important here called the reaction quotient. The reaction quotient. So let me show you where in the book this is. This is 621. This is quite important. And what this is the position at time 0. So this is the initial concentrations of the equilibrium. So we take the law of mass action and we look at the initial concentrations. And what's interesting is we can determine, so let's say we have the Haber process, right? We have the basic N2 plus H2, we have 3 of these. We could draw this the fancy way. And this becomes, of course, ammonia, 2NH3. And so to do the law of mass action, we're going to call that Q. We know what the K value is. If we have Q, we're going to say at time 0, so we use subscript 0, the product is NH3. We're going to put time 0 there. Remember, we have to take it to the second power. And then we have the reactants, so we're going to have N2 at time 0. It's like a subscript. We're going to multiply this by H2 at time 0 at the beginning of the reaction to the third power. And this is what we're going to get as Q, which we're going to call the reaction quotient. The reaction quotient. We can compare this to the known value of K. We know what the equilibrium constant is. And basically, if Q, what's kind of cool about this, is if Q is equal to K, of course, the system is in equilibrium. But if Q is greater than K, if this quotient is greater than K, say it's 3, and that's greater than K, I believe. Let's see, what was the K value for the Haber process? Well, no, it's actually a very large number. So let's say it's 3 times 10 to this 10th, which is definitely larger than K. And that means that the system has to shift to the left and consume products and form reactants. And that makes sense because the products are so much greater, right? The products over the reactants are so much greater. The equilibrium constant lies below 10 to the 10th. It's at 10 to the 4th, right? So the products have to form into reactants. Now, if it's the opposite, if the reaction quotient is, let's say, 3, and that's way below where it needs to be, which is 10 to the 3rd or 10 to the 4th, then the products have to grow and the reactants have to shrink. This number has to grow to be 3 times 10 larger than this number. And if you think about this for a minute, it makes a lot of sense. These concepts stand to reason if you look at the numerators and the denominators. So here's a fun and fancy problem. Same old idea, the synthesis of ammonia, and we know the K value at 500 degrees Celsius is 6 times 10 to the negative second, and we have to predict the direction of the system. And I only did A here, so if I do A and I put in the reaction quotient of the concentrations, I pop them in and I see it's 1.3 times 10 to the 7th. Well, that's way larger. That's way larger than the K value. So the products, and we know that to get a smaller number, the numerator has to drop. That's basic arithmetic, right? So the products have to drop and the reactants have to go up. So in fact, the reactants have to be more, the product of the reactants have to be more than the products. Literally the product of the reactants, otherwise known as the multiplication of the reactants, I don't want to confuse you, has to be greater, way greater than the product of the reaction. And that it has to be this much greater, 1 over that. So in any event, they do have to shift, and you can do the math out for B and C if you're so inclined. All right, let's look at 13.6, solving equilibrium problems. We're going to skip this section, so we can go to 628, 633, and when I skip pages in the book, I tell you which ones I'm skipping. This is basically the same stuff that we just did, except it's more math and more practice and more algebra. It does use the quadratic
formula a few times, so if I didn't want to overbear you with the quadratic formula, and you can go do those problems if you're so inclined. It is some more complex mathematics, but it's not so hard. All right, the final thing we're going to discuss is Le Chatelier's principle. And basically, this is just a common sense principle that if a change on a system that's already in equilibrium, let's say you have a system in equilibrium, the position of that equilibrium will shift in a direction that will compensate and reduce that change. So if you stress a system in equilibrium, the system will shift in a direction that relieves its stress, and that is a very simple concept. And maybe I should have added an example, I guess. An example. But you can take a look at the book in 13.7. You can maybe Google Le Chatelier's principle, and it makes a bit of sense if you think about it. And that's it for chapter 13. We'll see you next chapter for chapter 14 as we review chemistry. We're going to learn about acids and bases, so we'll recapitulate what we learned many chapters ago and maybe extend it a little bit into some more complex concepts. All right, thank you so much for joining me. I'll see y'all later.